white noise. Firstly, I'm going to write the post-spectral density of white noise. Post-spectral density of white noise. Post-spectral density is represented with capital S of omega, and the post-spectral density of white noise NT. It's a noise process. So I'm writing SWN. So it's an auto post-spectral density. This is given as N0 by 2, where N0 is a real positive constant. Real positive constant. So I can say that SWN omega is constant. Okay. So what is a post-spectral density? Can you tell me in simple words? Anyone? Please wait. Yes. What is a post-spectral density? Tell me in simple words. Post-spectral density. Are you with me? Can someone reply?
Distribution of power over range of frequency.
Very good, very good. Distribution of power over range of frequency. So, for better understanding, let us plot it, how it looks like. Y-axis is double n omega, power spectral density, and x-axis is omega. And the given S double n omega is constant. Am I right? It is constant. This is always n naught by 2. What is the meaning of this plot? What it represents? S double n omega is n naught by 2, which is constant. What it represents? Anyone?
For whichever frequency SNN is constant.
Yes. Very good. So the post spectral density is constant at all frequencies. Okay. PSD is constant. Can I say uniform? Constant is nothing but uniform, right? Uniform for all frequencies. At all frequencies. If you see the post spectral density at any frequency, that gives n naught by 2. If I say omega 1, the post spectral density is n naught by 2. If I say omega 10, the post spectral density is n naught by 2. If we say the at minus omega 20, the post spectral density is n naught by 2. So white means uniform. Here white represents uniform. The post spectral density is uniform at all frequencies. That's why the name is given as white noise. Okay, so let us write this informally. A wide sense stationary noise process. Here, what is a noise? Wide sense stationary noise process, capital NT, is called white noise. Is called white noise if its power spectral density S and S double n omega is constant or uniform at all frequencies. So this is the definition of white noise. Okay. Now, what is the relationship between autocorrelation and power spectral density? What is the relationship between power spectral density and autocorrelation function? PSD is the Fourier transform of autocorrelation function. We know the power spectral density is double n omega, that is n naught by 2. Okay, I want to know, we need autocorrelation function r double n tau. That means we have to find out the autocorrelation function from the power spectral density. How to obtain that? Which transformation we should apply? Anyone?
Inverse Fourier.
Inverse Fourier transform we have to apply. Very good. Okay. So what is the inverse Fourier transform formula? It is 1 by 2 pi integration from minus infinity to plus infinity. We are applying inverse Fourier transform on S double n omega e power j omega tau d omega. In the frequency domain, we integrate with respect to omega. In the time domain, we integrate with respect to tau. So we are applying the inverse Fourier transform on frequency domain. That's why we are integrating with respect to omega. Okay. 1 by 2 pi integral from minus infinity to plus infinity. Now S double n and omega is nothing but n naught by 2 e power j omega tau d omega. Anyway, n naught by 2 constant, move it outside. 1 by 2 pi integration from minus infinity to plus infinity e power j omega tau d omega. Okay, this represents from the properties of impulse function. This represents del tau. Okay, no need to prove it. This is del tau. Now, finally, the autocorrelation function r double n tau is equals to n naught by 2 del tau, where del tau is equals to 1. It is 1 at tau equal to 0 and 0 elsewhere. Okay. In time domain, del tau is 1 at tau equal to 0 and 0 elsewhere. In the frequency domain, it is given as 1 by 2 pi integral from minus infinity to plus infinity e power j omega tau d tau. Otherwise, you can write, but del tau is equals to 1 by 2 pi integration from minus infinity to plus infinity e power j omega tau d omega. This you will learn in the next semester in the subject signals and systems. Here you no need to prove that, just you write what is that integration, that is del tau. Okay, so the questions from this white noise processes define white noise and color noise. Okay, and draw the power spectral density of white noise. This one you have to draw. This plot you have to draw. Okay, and not only that, the question from this is derive the autocorrelation function of white noise. Derive the autocorrelation function of white noise. This one you have to prove that r double n tau equals to n naught by 2 del tau. So these are the questions from white noise. Not only that, you are asked to plot in time domain. In the time domain, x-axis is tau and y-axis is autocorrelation function. So this autocorrelation function is defined at tau equal to 0, which is n naught by 2. Okay. Now let us see what is a color noise. Color noise అంటే నాయిస్ లో కలర్ ఉంటుంది అనుకుంటున్నారు. Why it is called color noise? Different color has a different intensity, right? Different values. Different colors have different values. In case of white, the value is always constant. In white color, the value is always same. The value is same. But if you go from one color to other color, red color and blue color, so the values are different. The intensities are different. With respect to what it is given as color noise. This color is given with respect to power spectral density. So I'm writing the power spectral density of noise. Okay, this is a function of omega. When omega varies, the post-spectral density varies. What is the post-spectral density? Distribution of power. The distribution of power is varying with respect to frequency. At one frequency, the value is some value. Okay, at other frequency, it is having some other value. So frequency to frequency, the distribution of power is different. Like colors, the color value, one color value has one value, other color has other value. So with respect to that, here the noise is called color noise. If the post-spectral density depends on frequency, or if the noise or if the post-spectral density is not constant, or if it is varying with respect to frequency, that is called color noise. Am I clear? For better understanding, let us draw this so that we can easily understand. X-axis is omega, y-axis is double N omega. So here the noise is varying like this. See, the noise is varying. When the noise is varying with respect to frequency, this is color noise. Okay. Now, let us write this formal definition. If power spectral density of wide sense stationary noise process NT is not constant are varying, or not constant, or let me write it another way, is varying from frequency to frequency, then the noise is called color noise. Okay, so let me give one example for this. S double N omega is equals to 6p by 9 plus omega square. Now, is it color noise or white noise? Example ఇచ్చానని మనం చూడకండి. Is it white noise or color noise? If it is color noise, why it is called so? Anyone? Why it is color noise?
Function of omega.
Yes, very good. It's a function of omega. So let us see one problem on color noise. A wide sense stationary noise process NT has an autocorrelation function R double N tau is equals to P e power minus 3 mod tau, where P is a constant. Find its power spectral density. How to find power spectral density? Power spectral density, is it a time domain parameter or frequency domain parameter? Is it time domain characteristics or frequency domain characteristics?
Time domain.
Time domain. Is it correct?
Frequency domain.
Yes. Autocorrelation functions we have learned in the fourth unit. Fourth unit talks about time domain or temporal characteristics. Convolutional correlation functions and covariance. These are all time domain specifications. In the fifth unit, we are discussing about power spectral density. Power spectral density is a frequency domain parameter. So how to obtain frequency domain parameters? What transformation we are using?
Fourier transform.
Yes, just apply Fourier transform. The power spectral density is the Fourier transform of autocorrelation function. You can also apply the Fourier transform on cross correlation. That's also give the power spectral density, but that is cross correlation function. So whatever, you have to apply Fourier transform on correlation to find out the power spectral density. So what type of the power spectral density we have to find here? Auto power spectral density. So we have to apply Fourier transform on R double N tau, which is a autocorrelation function. So it gives us auto power spectral density S double N omega. So let us apply the formula. Let me write a formula of Fourier transform. It is integration from minus infinity to plus infinity xt e power minus j omega t dt. So in place of xt, we have autocorrelation function or double N tau. So let us write S double N omega is equals to integral from minus infinity to plus infinity. That xt here is R double N tau. In place of t, we have tau here. So we have to write e power minus j omega tau d tau. Okay. Now integral from minus infinity to plus infinity. R double N tau. It is already given. It is given as p times e power minus 3 mod tau. It is p times e power minus 3 mod tau e power minus j omega tau d tau. This is S double N omega. We are applying the integration from minus infinity to plus infinity. And inside the integration, there is a mod tau. This mod tau is tau for tau greater than 0. And it is minus tau for tau less than 0. Now here we need to split the integration into two parts, greater than 0 and less than 0. So S double N omega is equals to integral from minus infinity to 0, that is like t outside, e power 3 tau and e power minus j omega tau d tau plus p integration from 0 to infinity. So t tau greater than 0, we have to apply tau in place of mod tau. Okay. So p integration from minus infinity to plus infinity, we have to take e power let's take tau common. So e power 3 minus j omega tau d tau plus p integration from 0 to infinity. Here let us take minus tau common. So here we get 3 plus j omega tau d tau. So integration of e power 80 is e power 80 by a. So p here e power 3 minus j omega tau by 3 minus j omega. So limits from minus infinity to 0 plus p e power minus 3 plus j omega tau by minus of 3 plus j omega, the limits from 0 to infinity. So e power 0 is 1. So here it leaves us p by 3 minus j omega. And when you substitute minus infinity, so e power minus infinity is 0. So let's write minus 0. Coming to the second one, on substituting plus infinity, so we get e power minus infinity, that is 0, 0. And on substituting 0, we get e power 0, 1. Already there is minus, and we have to apply minus. Two minuses are there, so it becomes plus. So it is p by 3 plus j omega. So let's take P common, and I'm taking LCM or cross. I'm multiplying, so we get 3 minus j omega by 3 minus j omega 3 plus j omega. So j omega and minus j omega cancel this way and this way. So finally, it is leaving us s double n omega equals to 6p by. So we know that x plus jy times x minus jy is x square plus y square. So the same thing I am applying here. So we get 9 plus omega square. So this way you have to find the post-vector density when what we call when autocorrelation function is given. Okay. So any doubts in this?
Sir, second term is minus p by 3 plus j omega.
మైనస్ వస్తుంది, లోవర్ లిమిట్ సబ్స్టిట్యూట్ చేస్తే మైనస్ వస్తుంది కదా, ఆల్రెడీ డినామినేటర్ లో మైనస్ ఉంది, మైనస్ మైనస్ ప్లస్ అవుతుంది.
Okay, sir.
Just copy this. Did you remember the Laplace transform of un ut del t e power j omega t? Did you remember? Let me give you a table that is useful. Fourier transform pair. You have to remember this pair. This is very, very useful to find out the frequency domain or time domain. I mean to say Fourier transform or inverse Fourier transform. Yes. So first one I'm going to write this is xt time domain signal. After applying Fourier transform we get x omega. So the Fourier transform of del t is 1. What is mean by this? The Fourier transform of del t is 1. Or in reverse, the inverse Fourier transform of 1 is del t. In the forward direction, we are applying Fourier transform. In the reverse direction, we are applying inverse Fourier transform. So that's why we say that this is a Fourier transform pair. And del t minus t naught is e power minus j omega t naught, or del t plus t naught. This is e power j omega t naught. These are the Fourier transform pairs. And the Fourier transform of 1 is 2 pi del omega. The Fourier transform constant is the constant k times 2 pi del omega. The Fourier transform of ut unit step function is pi del omega plus 1 by j omega. And next, Sg and t. So this is called signum function or sine function. This is also called a signum function. It represents sine. So the Fourier transform of signum function is 2 by j omega, or in reverse, inverse Fourier transform of 2 by j omega is Sg and t. And the Fourier transform of e power j omega naught is 2 pi times del omega minus omega naught. And Fourier transform of e power minus j omega naught t is 2 pi times del omega plus omega naught. And the Fourier transform of cos omega naught t is pi times del omega minus omega naught plus del omega plus omega naught. And the Fourier transform of sine omega naught t is minus j pi del omega minus omega naught minus del omega plus omega naught. The Fourier transform of e power minus a t times ut, where a greater than 0, is 1 by j omega plus a. And the Fourier transform of t times e power minus at ut, where a is positive, a greater than 0 means a is positive, it is 1 by j omega plus a whole square. And e power minus a mod t, and a is positive, its Fourier transform is 2a by a square plus omega square. Our inverse Fourier transform of 2a by a square plus omega square is e power minus a mod t. So this table is used to find out what is the Fourier transform of first column. If you apply the Fourier transform on the first column, you will get the second column. If you apply the inverse Fourier transform on the first column, you will get the if you apply the Fourier transform on inverse Fourier transform on second column, that gives us the first column. Okay, simply apply the Fourier transform on time domain, it takes you to the frequency domain. Apply inverse Fourier transform on the frequency domain, it takes you to the time domain. So many are there, but these are enough. So how this is used? Let me give you one problem. Find the post-vector density of a wide sense stationary random process having autocorrelation function or double x tau is equals to half of e power minus a mod tau. Okay, So here you have to apply the Fourier transform on the autocorrelation function. So that gives us some s double x omega is equals to Fourier transform on r double x tau. Okay, so Fourier transform of half e power minus a mod tau. So anyway, half is constant, move it outside. Half Fourier transform of e power minus a mod tau. You can apply the Fourier transform formula, half of integral from minus infinity to plus infinity e power minus a mod tau e power minus j omega tau d tau, or you can use this Fourier transform pair table. So we have to use this formula. On applying Fourier transform on this, we are going to get this. It is 2a by a square plus omega square. Okay, here what is a? Anyway, a is there, so it is directly half. So after applying the Fourier transform on this, we get 2a by a square plus omega square. So this 2 and 2 gets cancelled. So finally, it leaving us. So it is leaving us as double x omega equals to a by a square plus omega square. Okay, so if you remember this table, it is easy to apply and find out frequency domain. Otherwise, you have to simplify this integration. You have to simplify this integration, right? Now find autocorrelation function of a wide distance stationary random process having force vector density s double x omega equals to 2 by 2 plus j omega. 2 by 2 plus j omega. So how to solve this? We have to find autocorrelation function, and given is s double x omega. So we have to apply inverse Fourier transform. So the inverse Fourier transform on 2 by 2 plus j omega. Anyway, move to outside, it is constant, f inverse of 1 by 2 plus j omega. So let us go to the table. So we need a formula which is in that form. So 1 by j omega plus a. So in place of a we have 2. So what is the inverse Fourier transform of 1 by j omega plus a? It is e power minus at ut. That one we have to use. So let me write that. So inverse Fourier transform of 1 by j omega plus a is e power minus at ut. Okay, where a greater than 0. Here 2 is greater than 0, so we can use that. So 2 times we can use e power minus, in place of a what we have 2. So e power minus 2 mod, it is an autocorrelation function, so we have to write tau u tau. So this is a r double x tau. This way you have to find, otherwise you have to apply inverse Fourier transform formula. Okay, any doubts in this class? Any doubts? Sir, are you there?
Yes, sir.